Welcome to the first HMEI Faculty Seminar of spring of 22. So this is, it's good to see that there are more and more people joining us in person, and we appreciate being able to do this also virtually. So today we have the pleasure to have Filiz Garip joining us. Filiz is a professor in sociology and public affairs who got her PhD at Princeton and then went and did a couple faculty stints at Harvard and then Cornell before rejoining us in 21, just last year. And we're sort of pleased as you can be that she is here. So Filiz has a whole host of accomplishments academically. One of them that stands out, at least in my eye, because is this book titled On the Move, Changing Mechanisms of Mexico-US Migration, which has received a whole number of great reviews, but also a lot of awards. In addition, Filiz was recently elected into the Sociological Research Association, which is quite a great honor. And very importantly, especially considering HMEI's commitment to sort of research and also teaching, is that Filiz has received great teaching awards, right? And so I think we're going to be treated to both some amazing scholarship and also presented in a way that we will actually learn and understand. So thank you so much for taking time to give us this presentation.
Thank you. Well, thank you everyone for being here. So I was told I could take the mask off unless there's anyone who's not comfortable. Is that okay? Okay, well, it's wonderful, wonderful to be here and wonderful to discover this new community at Princeton. So this is a new research area for me. So as Gabe said, I've been working on Mexico-US migration for a while, but until recently, I haven't really considered how environmental factors might have shaped this historical flow. So today's talk is all about that. So let me first acknowledge my collaborators here. So I'm going to talk about 4 interrelated papers. Don't worry, I'll go through them quickly. And all of this is done by this amazing team, who includes 2 economists as well as an environmental scientist and 2 amazing former students who now have faculty jobs. So the case is Mexico-US migration. So this is still the largest sustained international flow in the world. And if you look at 1980s, the solid line shows the number of Mexican-born people in the US. We had about 2 million Mexican-born in this country. And then you have this mass migration through the 80s and 90s. And by 2010, there were 12 million Mexican-born in the US. Half of them were undocumented, as the dashed line shows. So what brings these migrants to the US? Obviously, there are historical linkages. If you go back to early 1900s, you begin to see rail lines connecting central western states in Mexico to the Texas border, and employers going back to these places to recruit workers. And by 1942, actually, employers no longer need to make this trip because the US signs a labor agreement with Mexico, the so-called Bracero program, and the next 20 or so years, you have 5 million Mexican workers coming to this country for agricultural work. So the networks connecting migrants that are coming here back to their communities started developing as far back in time as that. And these networks definitely continue to persist, continue to transmit information and norms about migrating. And eventually, some sociologists argue migration has become kind of path-dependent and kind of independent of the economic conditions a bit because people have these social and cultural connections. So in this context, also we need to acknowledge there's still big economic differentials, maybe not as much as it used to be 30 years ago, but still most recent research shows that someone working in the US makes at least twice as more as someone who's observably identical in Mexico. So there are economic incentives. So what about environmental factors? So this is not something, like I said, that I thought about until 3 years ago. And the research on this topic started to kind of come out recently. And this research has mostly focused on weather fluctuations, how gradual changes in temperature and precipitation have shaped whether people move, where they move from. And then some of the findings are quite consistent across studies. For example, one of the earliest studies in 2003 linked low rainfall in rural communities in Mexico to more US migration. And the link they thought about was agricultural yields. So if it doesn't rain, then you have lower yields and more people migrate. They did not test this link directly, but then later our colleagues at Princeton, Van Kruggen and Oppenheimer tested this very link and found support for that. But then when you look at more recent work, you also see a lot of mixed and puzzling results. So I'll just give one example. Rioswena and colleagues also think about rainfall in Mexico, and they connect it to more US migration, but they also find that this only occurs in well-off communities, so relatively wealthy communities. And the explanation is that you need resources to cross the border, so only these communities can finance the move. But then they look at the temperature, and they find that heat extremes have the opposite pattern. Now you have a migration response, but only in very poor communities. And it's very hard to explain these patterns. So this is just one example, but it shows us that we actually have a long way to go to come up with credible and consistent results. So this is what we're trying to do with this project. And we see several steps to getting there. First obstacle that we need to address is you need highly granular data. So most of the research measures weather at kind of these coarse regional units like states. But you can imagine how big a state is, and you can imagine how the weather can vary within that state. So we want to overcome that. We also want to measure migration at the individual level, not just aggregates, how many people in total migrated, but who actually was migrating. Second, we need to choose the right weather measures among almost an infinite number of options. So how do we know which measures are the most relevant? And then we need to think about mechanisms like the agricultural link that Fang and others were talking about, because we want to design policy interventions, hopefully to mitigate the migration pressures created by weather. We also want to think about potentially complex relationships, right? So you might imagine things like intensification or decaying of effects. So imagine a community has irrigation, so if there's 1 year of drought, nothing happens because they have water, but then if there's consecutive years of droughts, you might suddenly see this impact. So we might call intensification. Or you might observe the opposite, right? A community experiences a few years of drought and then adapts, divests from certain crops, and then you no longer observe the weather impact. So we need to think about that. And then we need to kind of think about heterogeneity. Not all of us respond the same way to the same situation. And that's where having individual level data is important, because we can see who in our population is most susceptible to these shocks. And then, because migration is such a complicated decision and there are so many policy things affecting it, we also need to think about how US trade policies and migration policies interact with potential weather-created migration pressures. So this is the goal that we're setting to ourselves, and we're not kind of meeting all of these goals, but that's kind of where we're headed. So the migration data comes from the Mexican Migration Project, and this data set actually has been collected by one of our own sociologist Doug Massey and his collaborator back in Mexico, Jorge Durant. So they started this project in 1982, and right now we have information through this data on about 140,000 individuals in Mexico, over 170 communities. And about 20,000 of them have migrated to the US at least once. More than 80% are undocumented. So these are all hard things to measure, especially undocumented migration. So this data set captures that. So the way they collected the data is they went to each community once, and then they canvassed the community and they selected 200 random households. And then in each household, they collected information on everyone, even absent migrants. And this information was like a life history. So what were you doing when you were 15, 16, 17? So although each community is surveyed once, we can create a pseudo-panel data set because we have this retrospective data on individuals. So this is what we're doing here. And then we're observing the individuals between 1990 and 2018. We can go farther back in time, but the weather data with the granularity that we want starts later, so we just cut it off there. This gives us about 1 million person years, because each individual is observed in multiple years. So this is a quite good data set. Now, we combine this with high granularity weather data that comes from DayMet, and this is gridded data that covers every kilometer square space grid on Earth, and then it provides daily measurements of precipitation and temperature. And this data set is available from 1980 onwards. Basically, what we're doing is putting these two data sources together. So imagine that you have a community boundaries here, and you have various grids that fall into it. So you can basically create these average measures at the community level, which will give you daily measurements. And then you can create more kind of aggregate measures, like seasonal versus annual measures using this information. Now, we think that this granularity of the data, which we made a big deal out of, and we spent almost a year thinking about this, is really, really important. So let me just give you one example. So we're looking at number of days over 30 degrees Celsius in these Mexican states, and these are basically very hot days, right? So we're counting them in year 2000. And then we're comparing each community to its the number of days it observed its own self. So basically, we're taking the values in year 2000, and then we're looking at back between 1980 and 1984, how many days of hot weather were observed. And then we're kind of looking at the difference between them and dividing it by standard deviation. So basically, this is asking, in about 15 years, how many standard deviations are you off from your average? And then we see that if you get the orange color, it means you're slightly hotter than the past. If you get the bluish color, it means you're slightly cooler. And almost all of the states are slightly hotter. But then if we look at it at the municipality level, we see a lot more variation. So these little municipalities in that kind of red rectangle, you see they actually experienced extreme heat. But then because we averaged them over the state, we weren't able to see this. So the communities that we're seeing in the Mexican Migration Project are a lot smaller than municipalities. So this is really kind of high granularity data, and we actually tested this, how much of a difference it's made if you measure it at the community level, municipality level, state level. Huge difference. Now, this brings us to the question of how do we measure weather, right? So we kind of looked at only one measure here, counting the number of days over 30 degrees Celsius, which a lot of people do in the literature. But there's so many different alternatives. And we actually spent a lot of time also thinking about this. One idea that we came up with was basically having this data-driven choice. So we used supervised machine learning to pick the most predictive measures of migration behaviors. So supervised machine learning is basically a statistical method. It fits complex functions in order to link your input, in our case, the key input is your weather, to outputs like whether someone migrates or not. And the method that we're using is based on the so-called regression trees. And hopefully it will make sense kind of why we had to go in this way. So basically, these models describe a tree-like structure that describes a sequence of splits in your input space, in your X, that predict Y at the end node. So I'll just give an example. The reason that we like this methodology rather than having a linear regression is because we can think about non-linearities and interactions across things, like really complex structures that we wouldn't necessarily able to kind of describe parametrically. So let's say that we're interested in migration, 0-1 outcome in this case, and then we have two kind of key indicators, age and education. So a regression tree might work like this. First, it would split your data by age, young and old, and then you can imagine each branch splitting again, this time by education, and at the end of each node, you might have a prediction. So in this case, we see young and college-educated migrating. Now, the models we use are a little bit more complicated than that. They're called random forests, and you can imagine a forest includes many trees, so basically it's averaging over thousands of trees. It does that in order to improve predictive accuracy, so fitting more and more and more complex models, and then hopefully this improves your predictions. But then you lose something on the way, you lose kind of interpretability of the model. So you can basically link some weather measure to migration, but you don't exactly know how that relationship works. So not all kind of advantages. So the output we're interested in is first US trip. And then the inputs care about individual characteristics like age, sex, and education. We know this really matters. People are selected on these attributes. People are also selected on household properties, whether they can afford the journey. Also, household migration experience really matters, which is kind of we can compute in this data set. We also care about community attributes, like the share of people working in agriculture or share of people with US migration experience. So in some of these communities, if you can believe it, 70% of the people living in that community have migrated to the US. In other communities, only 10% have migrated. So there is a difference between these two settings. And our key interest is basically measuring weather. And we're computing weather in deviation form, so we're basically comparing each community to its own normal. And then we basically looked at the literature and added every measure that we could find. So this gave us over 30 plus indicators. And we can compute these indicators in different ways. We can compare a community to its own normal 20 years ago versus 40 years ago. So kind of long-term norm versus short-term norm. We can measure these indicators annually or seasonally based on what crop a community is growing. So we might worry about weather in that particular time period. We can also include, because these models technically will tell us which indicators are most predictive, we can include many lags, which would be hard to do if we had a linear restricted model. So here we include a 5-time lag. So we're going back 5 years ago and see if weather 5 years ago really matters or if it interacts with kind of other lags. Now, the weather indicators, as I said, are available from 1980 onwards. So we reserve 1980 to 1984 period as the normal period. So this is the period that we're going to use as our baseline. Now, this will probably tell us that our data can start, or analysis can start in 1985. But it's not exactly right, because I said we need 5-year lags. So then this brings us, this basically forces us to reserve this period to be able to compute the lags. And then our analysis really starts in 1989. And it comes down to 2016. Now, this is a little bit in the weeds, but kind of let me try to kind of rush through it a little bit. When you fit a really complex model to your data, you always run the risk of over-explaining or overfitting. In other words, with a complex enough model, you'll pick not just the signal in your data, but you'll also pick the noise. So with random forests, with a complex enough model, you can basically explain every data point, fit it perfectly. But what do you lose? If you had a new data set, if Doug Massey came and said, I have 10 more communities, can you predict migration here? It wouldn't fit there because it wouldn't generalize. It's learned the data so well that it doesn't explain much outside that data. So we want to prevent that, and this is very typical in machine learning models. So this is the way we do it. We have, after all these time restrictions, we went down from 140,000 individuals to 54,000 individuals, and we're observing on the and we're observing each individual over multiple years. Now, supervised machine learning models, it's not like in a typical regression setting, you can account for clustering in your data. So you can say, if my ID is 1, if I have 10 years of data points, so I can tell the model that all 10 data points come from the same individual. But with these models, it's kind of trickier to do that. We have the same individual, me, observed over 10 years, but the model would not know that. So to get over that problem, there are many solutions, but we basically converted the long format of the data, where each row is a person year, to a wide format. So every person is represented once, but we code the entire history of that person and the weather they've been exposed to in the columns. So we keep migrants in our data on the year of their first trip to the US, and for non-migrants, we pick a random year among their observations, and again, code the history in columns. Now, in order to avoid this issue of overfitting, the way you do it is you basically set aside a portion of your data, and you use that data set to fit your models, fit different models, and then compare different models and select what you think is the best one. And then you set aside a different portion, the so-called test data, to see how well your data generalizes to this new kind of portion of the data. So that way, you're trying to avoid overfitting, and you're also trying to be kind of less optimistic, because if you just evaluate your model on the same data that you use to estimate it, you'll always get kind of overly optimistic results. So what we did here was we took 40,000 individuals and we set them aside for training and validation data. And we did, the cross-validation procedure. You basically take a random portion of your data, fit the model, and then test the predictive performance on the rest of it, and you cycle through your data. But then there's a portion of the data that we didn't touch until everything was done. So this is where we evaluate how well we actually did. And 14,000 individuals were kept in the vault for that. So all the results I'm going to show is based on the test data. So this is the data that the model has not seen. So what do we find? Okay, so hopefully this is not going to be too boring, but this is a graph that we look at in order to evaluate and compare different models. So on the y-axis, we see the true positive rate. So these are the migrants that our model correctly identified and classified as migrants. So we want to maximize that. And then on the x-axis, there's a false positive rate. So these are the cases where our model thought, here's a migrant, but in fact, that person was a non-migrant. So basically, the curve here is what happens to your model when you shift the discrimination threshold you're using in your model. Basically, it's showing us that there's a trade-off. We can make our model true positive rate 1, but then we would have also a lot of false positives. So why am I showing you this? Because if you compute the area under this curve for each model, it gives you a performance metric, predictive capacity metric. So let me kind of tell you, in the solid line here, we're seeing the curve for the model with only individual level factors. This is our best performing model with individual level indicators alone. And we see that the area under the curve is 0.79. So a perfect model would have an area under the curve of 1, which means that it can perfectly separate migrants from non-migrants. With this model, we can separate them 79% of the time. So in 79 out of 100 cases, we're correct. Our model is correct. What happens if we include weather indicators? How much, adding all these weather indicators, I think about 200 of them, improve our predictive capacity on the test data? We see that with weather indicators, our area under the curve is 0.81. So we have a gain of 2% in predictive performance with all of the data included. Which is, depends on how you look at it. You can say, wow, we've gained 2%, or you can say all of that for just 2%. But the reason we're able to see this is because we're looking at the test data. If we computed these things in the training and validation data, they're much better, right? So this is like, really you face the reality of your model. Now, this is not exactly the reason we use these models. We wanted them to tell us which weather measures were the most predictive of migration choices. Now, here's some results on that. Again, this is computed on the test data. And the way we do it is very simple. Now that we understand what area under the curve is, we take the test data and we say, what if I recoded gender? What if I randomly assigned people gender instead of the actual data? What if I corrupted that indicator? How much do I lose in terms of predictive capacity? So we see that if we corrupted the gender information, male, we would lose 7% in terms of predictive capacity. So that's huge. That tells you how important that feature is in predicting migration. And you can see the next important thing is whether there are other migrants in the household who can help you migrate. Other things like age, whether your family owns property so that they can finance the move, they're all important. What about weather indicators? There are a few that consistently outperformed others. And we were actually a little bit surprised by that because some of these are really generic measures that don't require any sophisticated thinking. Warmest night temperature in a year mattered. Coldest day temperature. And also, this is less surprising, a very customized measure called growing degree days. So this is literally counting the days that are optimal for the growth of corn during the corn season. So, this is actually important. The other surprising thing that inspired another question was to see how much other policy indicators mattered. If you look at the blue rectangle, the amount of trade between Mexico and US is really high up there. And this is something that changes only annually. It doesn't have much of variation, and yet it's able to account for the trend in the data. So I'm going to come back to that. So basically, the backstory here is in 1994, Mexico signed NAFTA with the US, and it's opened its doors to US imports for corn. So many people argue that this actually hurt smallholder farmers. So we're going to talk more about this, but for now, just let's take a note. So seeing that growing degree days really matters gave us kind of the second path. Instead of asking the data, which ones are most predictive, let's think carefully about what would be particular mechanisms that we would want to test. And here, like Oppenheimer and colleagues, we wanted to focus on agriculture. And corn is the biggest crop in these communities. And we wanted to think about how corn grows, what periods are most important, and can we capture that with data. Now, again, this wasn't as simple as we thought. There are many alternative ways of looking at corn seasons. So if you look at the Mexican agricultural census, they distinguish between two periods. So they say rain-fed production happens between April and August. Irrigated production happens between November and February. So we use these. But then we found more detailed crop calendars that are region-specific. So in most places in Mexico, the full planting to harvest cycle is between May and December. But then in the south, like Yucatan, it's actually June to February because the weather there is different. And then in the northern and western states, it's September to March. So we considered all of these different possibilities. What if we measured it this way or that way? What if we measured just the planting cycle versus harvesting cycle? And again, it just turned out to be more complicated than we initially thought. And again, because we're interested in this agricultural mechanism, we excluded urban communities. So we're now down to from 170 communities to 93 agrarian communities. So in these places, about half of the population work in agriculture. And most of them, but not all of them, grow corn. We took the normal period to be a slightly wider window because we're no longer doing 5-year lags, because we're going to kind of come up with parametric models, carefully thought out models, rather than really complex models that we can't interpret. And then we computed, again, weather indicators as deviations from the community normal. So again, the normal period is 1980 to 1990. You look at the mean value of your weather indicator there. You look at today's value. You take the difference, divide it by the standard deviation. And then we categorize this. So categories are pretty obvious. We considered a place was very wet in a given period if it received more than 2 standard deviations higher rain than its average. And then wet is between 1 and 2 standard deviations, and a similar categorization for temperature. Okay, the outcome again is first US trip, but this time we can include person-year observations. So we're no longer kind of using the wide format. Okay, so we write a model where the first US trip is a function of precipitation and temperature in the previous year and the year before that. So we can't go more complex than that because then the model gets too complicated. And then we include the additional controls at the individual household and community level. And here we use a linear probability model, which means that our outcome is binary, but we don't use a nonlinear transformation like a logit for our outcome because we want to effectively control for state by year fixed effects. Now, what does that mean? So adding these state by year fixed effects means that we want to control for temporal changes that might be region specific. So let's say that the state of Sonora experienced a trade shock, which it did after NAFTA. We want our model to absorb that, which means that the variation we're looking at now is differences between communities. So the same community is experiencing everything else being equal. Is there a difference between communities depending on what they observe? Now, some findings, again, are very reassuring and have face validity. So basically, we find that extreme decline in rainfall increases the odds of US migration. But then we also find that, remember we tried different measures, annual, seasonal, different kinds of seasons. Rainfall deficits during the corn growing season are more predictive, matter the most. And we also see that if we kind of hone in on the mechanism better and better, if we exclude communities that are not doing kind of corn as their major crop, our effect sizes get bigger. So the effects are really concentrated in corn growing places if they experience weather shocks during the corn growing season. So this is just an example of some of the models. So the effects are slightly larger in corn growing communities. Interestingly, heat here does not really matter. And it's mostly about rainfall. Now, some more interesting results. We also find that drought effects intensify over time. So what we're seeing here on the y-axis are the marginal effects of different weather conditions. And then on the x-axis, we have different rainfall combinations over time. So what happened 2 years ago and what happened last year. So in the first one, we see it was normal and wet last year, but dry 2 years ago. So we're just looking at sequencing of things. And you see the big jump in effect size when you have 2 consecutive years of dry weather. So that's when you see kind of the biggest jump. You also see that there's differences across communities. If a community is irrigated, they don't experience the same kind of intensification. But if they're not irrigated, which are kind of the empty circles there, you see this big effect. Now, what does this tell us? It tells us that if we do something after 1 year of drought, then we can basically intervene and alleviate the weather shock. This also said if we invest in the long run in irrigation, that also makes a difference. That allows communities to weather these shocks. We also find that cumulative effects vary by household wealth. So rich and poor households respond differently. And in this context, no household is truly rich. The way we define rich is if you own anything, like a piece of land, property, a business, which could be a taco truck, like something very simple. And 80% of households actually own none of this. So they're considered poor in this setting. So here, households without assets are the empty circles, and those who have one asset are the filled circles. So we see that households with assets can respond immediately to a weather shock. So you experience a shock last year, you can immediately migrate. So the effect is positive after 1 year of a shock. If you look at poor households, they really respond after 2 years of consecutive shocks and actually worsening shocks. And rich households respond to that as well. So again, it tells us that some people will be able to respond to these things, use migration as a potential adaptation strategy much quicker than other households. So basically, the takeaway lesson is weather effects are not just cumulative, but they're also heterogeneous. Now, we basically thought about 2 alternative ways of thinking about weather measures. Something that we also wanted to do was ask people, right? So what if we're missing something? What if there are things that we're not capturing or measuring correctly in our data? So this is right before COVID. We went to Mexico, and we did field work with corn and coffee farmers there. And many interesting things came up. But this one we hadn't thought of was people were talking about how weather now comes in different combinations. So this farmer says there was a change that now it rains, and when it rains, it gets hot. It used to not get hot. So this gave us the idea of thinking about interactions across different weather measures, heat and temperature, and we found that this really matters. The farmer was right. Drought, when it's combined with extreme heat, has a much higher impact than either condition alone. Now, 2 extensions, I think I'm like 3 or 4 minutes away from finishing up, but 2 extensions that we're working on. So one of the questions that we wanted to ask was, does extreme weather actually affect where migrants cross from? So this data that you're seeing here is showing the crossing patterns of migrants in our data. So basically where they cross from the border and then where they end up. So basically we wanted to see if experiencing extreme weather in a community would push migrants to take unnecessary risks, basically cross from spots on the border that were potentially dangerous. And Border Patrol basically defines these different regions on the border as sectors, and there are 9 different sectors, and each of them are very distinctive in terms of your likelihood of being able to cross without documents, without being detected, your likelihood of dying due to natural conditions, and the costs of smuggling. So let me kind of give you an example. Like the shorthand is the sectors that are easier to cross are usually deadlier for people. Now, the 3 most popular sectors in our data are Tucson, San Diego, and El Paso. And let's start from the Tucson one. So you can see that this is the easiest to cross, meaning that it takes on average 1.1 tries to cross the border, but it's also the deadliest. About 3 out of 10,000 migrants die trying to cross the border. Now, this also is reflected in the smuggling fees. In order to kind of navigate these dangerous spots like Tucson, you have to pay higher. So we think that this will matter in kind of where migrants actually cross from. And we're thinking of this in terms of credit constraints. And here, kind of, I'm talking about we, but this is mostly a model written by Nancy Chow, the theorist in our group. And she wrote a model of sector choice, or like how migrants would consider different options of like where they cross from, like risk versus rewards. So the formal model comes with some implications. And the biggest implication is credit constraints would matter. So migration is really costly in this setting if you're not documented. The smuggling fees are around $5,000. Again, there's a variation depending on where you want to cross from. But we think that anything that will create migration pressures, plus anything that will affect how much money is available to you as a family to finance migration, will matter on where you cross from. Now, we're considering a couple of things. We're considering weather as a big shock, but we're also considering trade as a big shock. And then we're also thinking about border enforcement, because that also determines the costs of crossing. And there were sector-specific operations, basically very targeted operations that Border Patrol did over time to stem the migration from a particular region. So we're basically controlling for that. Now, I talked a lot about how we measure weather shocks, measuring trade shocks. It was good to have economists on the team. So we computed something called Import Penetration Index. And again, we wanted to capture this not at the country level, not at the state level, but something at a more kind of granular level. And we used municipality level data for that. And basically, this is a function of a couple of things. The first thing that goes into the index is the ratio of your labor force in the municipality that's working in agriculture. So we're just interested in agriculture here, how much imports affected agriculture. And we're taking the ratio of that, share of your labor force in agriculture, to the overall ratio of agricultural workers in the country. So how much more invested is this municipality in agriculture relative to the rest of the country? And then we weight this by changes in trade imports. So basically, value of imports in agriculture as a share of the GDP. So basically, the higher the country is involved in imports, and the higher your kind of investment in agriculture, the higher the impact will be. So this gives us a way of measuring trade shocks. And they seem to really matter. So this is a very coarse summary of what we find. If we start with the middle row, we're looking at particular operations that Border Patrol did on the border. So Operation Gatekeeper, which targeted the San Diego region. Clearly, it's kind of directing people away from San Diego. So there's a negative impact there. If we look at import penetration in agriculture, we see that there's a negative effect on selecting Tucson. So this is how we think it works. When you experience a shock, an import shock to your community, your income is likely to go down. This means that you can no longer afford the smuggling fees of Tucson, which are more expensive. So this is directing you to cheaper locations. And rainfall actually has an interesting effect. So here we see that receiving higher than average rainfall to your community, but not extreme, is actually increasing the chances that you'll take the more expensive path. And here we think that it's actually relieving credit constraints. It's giving you money. If you had favorable weather the previous year, this means that you were able to save, and now you can use that saving to migrate. And this is actually an interesting finding that aligns with what other people explained, both in this setting and other settings. So until now, we thought about weather as a constraint. So you experience this shock, and migration becomes a way of solving that problem. But actually, weather can also be a resource. So if it's favorable, if it allows you to save, then it gives you the resources to migrate. And actually, in a lot of places, people observe this pattern. Actually, receiving some injection of cash does not immediately reduce the odds of migration. In the beginning, it increases it because people can see migration as an investment. So this is an interesting result. And then one final thing. Most of the questions I asked until now all had to do with decision to migrate. What makes a person migrate? But what about duration of stay? Does experiencing repeated bad weather events back home make you stay here longer? So this is what we're asking here. I'm not going to go into the details, just describe the results. We find that actually continuing extreme weather in origin pushes undocumented migrants to stay longer in the US. And the effects actually persist over many, many, many years, not just the first few years of entry, which tells us that migrants here are constantly watching, monitoring what's happening back in the community and are not returning unless the conditions are right. Now, main takeaways. The first one is clearly migration in this setting offers an adaptation strategy to weather. When things are not favorable back home, coming here allows people to finance farming back home, and many migrants actually eventually return if the conditions are right again. And we also see there's heterogeneity, right? So rich households can respond in this way, can use this adaptation strategy a lot faster and more safely because they can finance crossing from safer locations compared to the poor. And for poor, they have to experience more events in order to be able to come. And then we also see both enforcement policies and trade policies may exacerbate the adverse impacts of weather fluctuations and climate change, especially in poor communities in the developing world. Some analytical, takeaways, as I said, like the level of aggregation really, really mattered here. The higher the granularity of the data, like the more precision we can bring into kind of how we measure things, the more we think about mechanisms that the weather impact works through, I think the better we can capture these patterns. And also kind of looking at heterogeneity across people is really, really important, and then using different methods. So this is definitely a mixed method study that reflects many different disciplinary backgrounds that we bring to the table. We've used anything from formal models to parametric statistical models to predictive modeling and qualitative data. And I think we've learned something from each of these approaches. So thank you so much. Looking forward to hearing what you have to say.
Well, we will now open ourselves up for questions and discussion. I will. I have a question here in the chat, but I welcome any more questions online. If you have questions online, please enter them into the Q&A. And if you have questions here in the audience, signal in some manner. Okay, so the question that came online, Filiz, was what about the ups and downs of the drug trade and sort of the impact of crime? Do you see any evidence of that, or was that taken as a fixed effect, or?
Yeah, so I mean, that's such a good question. So in the parametric models, that would be observed by the fixed effects. If there's a sudden increase in crime rates in a particular state, then this is not something that we're necessarily measuring, but we're hoping like the state by year effect will absorb that. But these data actually are not that great for capturing this later period of Mexico-US migration. So the data set, because it's kind of based on these retrospective life histories, it has great coverage between, say, 1985 and 2005, 2010. So some of the biggest jumps in crime rates in Mexico happened after 2006, when President Calderon started this war on drugs. And there were turf fights and crime rates really spiked. So we tried to look at that, the impact of that in our data, but we don't have enough of a data from communities that happen to be in that region in that period. But I think that's a really, really important question, especially like in the border region. After 2006, there was a huge increase in homicides. And also, it's kind of hard to separate the effect of that from the effects of NAFTA, which impacted the same region, the border region. So we have these two forces coming together in that period, but our data are really not ideal for that question, but a great question, yeah.
So nobody has given, oh, I see a signal here. So I'll get the question and I'll repeat it on the mic. Yeah.
Thank you for your talk. It was really interesting. One of my questions was on the kind of comparison between urban and rural areas. I think rural areas will be more dependent on the weather fluctuations, since a lot of people will be more likely to be working on agricultural crops and those kind of things. So, did you find any differences between rural versus urban systems?
So I'll repeat the question into the mic so the audience can hear it. So the question is about differences between rural and urban areas, and are there any differences in the effects between rural and urban areas?
So rainfall does not matter in urban areas. Rainfall only matters in rural areas. But we've actually gotten some signal that heat in the city matters. The thing is, I'm happy to report it in a paper, but it's hard to explain what mechanism it works through. I think yes. I mean, the short answer is yes, you can detect some of these signals in the data, but sometimes it's kind of hard to explain what's happening in those communities. Yeah, I mean, if you have any ideas, I would be really, really happy. I have colleagues in the environmental sciences that have used pollution and other indicators that are not exactly weather, but still kind of environmental. So there's some evidence of that. There's a rich literature in economics looking at the effect of heat on economic productivity. So, I mean, within that line of work, I can fit some of these findings maybe, but yeah, that's something that we're still kind of thinking about. Yeah.
So riffing off that, there are two questions here. One from Colin Hickey, asking more regarding the conception of what rich is, right?
Yep.
Which seems to be a pretty relatively low bar. Is there a threshold above that where you might see that the effect changes again, where the pressure to migrate is not there, and you know what might that tell us about policy interventions? And then related to this whole question of digging in deeper, have you looked at the potential effects of weather shocks at the destination of migration on the decisions?
Yeah, great question. So yes, we have looked at wealth we try to look at in a more kind of graded way. And the best measure we found was counting the number of rooms in the properties they own, because you don't know the value of the property. There's no way of guessing that. And basically, but then people report, okay, I own a house and there are 4 rooms in my house, or there are 10 rooms in my house. So we categorize people. Again, 80% have 0. But then the remaining 20%, we divided them into 3 categories. What if you have 2 to 4 rooms, 4 to 6 rooms? And then there is a nonlinearity, right? So it's like having a little bit increases your chances of migrating, but if you have a lot more, then you don't migrate anymore. And this is like a very typical pattern in the migration literature, that it's the middle income, middle wealth families that both can afford to migrate and want to migrate. Because for other people, they don't want it. So the destination is not something that we've looked at, but we should, right? Because, I mean, obviously, weather fluctuations are impacting agriculture here, and agricultural labor coming from Mexico would be impacted by that. So the destination data are not perfect in the sense that you know where people came to and their first point of entry here. So you know if they ended up in California, Chicago, somewhere else, but then you don't know if they've moved within the US. That said, I think it's still worth doing. You also know the sector that they work in, so you can at least separate agricultural workers from service workers and see if there's a different impact.
We had a question over there.
Hi, I just wanted to thank you for this talk. I am a child from both undocumented immigrants and from the federal program, so thank you for this talk. And also my professor here models the physiological stress of crossing this region, mostly the Sonoran Desert. And he really actually measures the evaporative water loss. And so he noticed that there's a difference between sex, age, and reproductive status. So I was wondering, do you think the different behaviors in the different communities, like the lower income and higher income, may be just differences in who's migrating? So maybe the lower income communities are mostly men who have like a higher thermal tolerance and are able to pass by those times.
Yeah.
So let's see if I can encapsulate it. It's a good question. So there's physiological differences in the sensitivity to weather driver stresses on people, and the question is, to what extent are the differences in demographics behavior of the behavior driven by differences in sensitivity that can be mapped onto that to weather? Yeah.
Well, thank you for coming to this talk, and I would love to talk more about this. So, I think that's a really interesting question. I kind of, as a sociologist, I have to say, I wonder about how much of this is cultural, like who can bear what kind of stress and dangers, and how much of it is like actually physiological ability to endure. But there are obvious differences, right? So usually when women migrate, they don't cross from the desert in the data, but they use entry points. So they will use someone's passport who looks like them, and they won't take unnecessary risks. And men, and especially younger men, are much more likely to kind of try out more dangerous places that are supposedly easier to cross. So there's kind of definite differences there. I don't know, definitely maybe physiology is what underlies kind of cultural perceptions, but there are differences. Also, I don't know if you kind of caught this on the map, but people don't take the shortest path. So there was a time when we were thinking, okay, so let's compute the shortest distance between where they're coming from and where they're heading. No, kind of most people go all the way to San Diego, and then they will go to, I don't know, Chicago from there. And that is also kind of a process of networks, right? So if everybody in your community crosses through there, you just follow them. And people also kind of in field work talk about how they can't trust just any smuggler, so they need to find a smuggler through friends, and somebody has to vouch for them. And this is where the crime question actually is really important. The drug trade actually also affected, smuggling operations. So in the past, in the 1970s and 80s, smugglers were prior migrants themselves, and they would charge kind of very little money, if at all. But then, cartels or organized crime became involved in human trafficking or kind of smuggling migrants across the border, and then it became really dangerous for migrants because these are people who carry guns and leave migrants in the middle of the desert. So that also kind of changed things. But yeah, I appreciate the question, and I would love to hear more about the research.
I saw some movement here, but there's a question from Michael Oppenheimer. Congratulations, a lot of great progress since 2010. One surprise from his perspective is that temperature variations did not seem to matter as much in your study, where in other studies they had a comparable impact to precipitation. Do you have a sense as to whether that is due largely to using different temperature measures, the resolution in the data, or I don't know, do you care to speculate?
Yeah, so yes, it's possible. And then our specification, I mean, the one at least I presented is a very particular one, basically wiping away all state by year variation and just looking at between community variation. So if we were to fit the model separately to rainfall and temperature, we detect some temperature effects. But whenever there's rainfall in the data and we kind of plug in temperature does not have an effect. And this might be due to correlation between the two. But then, like I said, when we interact the two, that kind of increases the effect of rainfall. So there's something there, but yes, it might be differences in measurement.
So we have a question here. Yeah.
Thank you so much for such an interesting talk. I was just wondering if you had thought at all about how people might be responding not just to weather shocks, but also to changes in beliefs about future climate that they might be getting from those weather shocks, or if you could anything else about that.
Yeah.
So, yeah, very interesting question. The question is, to what extent are people responding to weather and past and present, and to their beliefs about future weather?
Yeah, hard to say. So this comes up a lot in fieldwork, obviously, when people talk about this. And when we went there in 2019, I was actually quite surprised. So we didn't design the question so that we would ask about climate change or weather. We just kind of asked about their kind of how the farming is going and kind of who's migrating and so on and so forth. But then climate change was the first thing that they mentioned, that things are different now. There's a lot more variability. We don't know when summer is going to be. We don't know what next year is going to be like. And some people think it has to do with how well advertised this is in Mexico, and people are constantly getting the message that things are different. So I can't separate the two, but there's definitely grim prospects or expectations from the future playing a role in how they talk about this. In terms of like measuring this with data, I'm not sure. I think one thing that we haven't done is looking at how variability matters. So we've looked at sequencing of events, but maybe one way to look at it is like some sort of measure of variability over time and whether that affects how people act. But yes, great question. I haven't figured it out yet.
So we have one question here online, the Sarah Constantino asks, wondering whether there's any back effect from migration onto other more in situ adaptations. So is there a relationship between households with people migrating
Yep.
and then investment in irrigation systems or other measures to create local resilience?
Yes, so we're just starting to look at this, so I can't answer definitively, but we actually have some measures of remittances and what share of families are receiving remittances in the community, how much remittances are reaching which community. So right now we haven't found any signal yet. We've kind of put it in our models, but yes, that's kind of the direction that we're looking at. And then irrigation, sadly, is not measured over time. Irrigation is only measured in one point. So we've obtained administrative data from Mexico, the Mexican government, that at the municipality level measures irrigation, what's being planted over many, many years. So we're hoping to use that as well.
Okay, and we had a question here. Yeah.
I used to live and work in Tucson, and in 2018 we saw a big influx in asylum seekers, and especially women and children who were just like turn themselves into the border.
Yeah.
And I was just curious if your study looked at how weather kind of influenced asylum seekers in different complications from migrants or something.
Yeah.
So the question was, is there a signal in asylum seekers at the border from weather in the data?
Very few asylum seekers in this data. So they're undocumented. I mean, there are a few of them. There are a few kind of temporary, so yes, no, we can't look at it. Yeah.
And then I'm looking at the time, and we're running on time, and they're great, interesting questions. Thank you, everybody. There was one question about the effects of industrialization. If, for example, are migration rates lower in more industrialized communities? And so is there any relationship to industrialization?
I'm not sure. So we have a measure of, in the data, we have a measure of a percent of the population working in manufacturing, which could be considered a measure of industrialization, and that's available over time. So we can see how communities have shifted from agriculture to manufacturing over time. It didn't do much for this, but we haven't tried interacting that with weather, actually. So maybe. I'll look at it, is all I can say.
Okay, well, I see Morgan pulling out the hook here, and so we're going to be chased off. But first, I really wanted to take an opportunity again to thank you, Filiz. This has been wonderful. Very engaged audience. Thank you very much again.
Thank you all for coming. Yes.
And then a reminder that on March 1st, Blair Shaney from Department of Geosciences will be joining us here to be our second speaker for the semester. And thank you for coming, and looking forward to seeing you again in March.